Welcome back, everyone, to this seminar on the phone calculus, a process calculus, a general process calculus with support for data embedded into Isabelle Hall using higher order abstract syntax. So we are still in this part where we discuss the transition system framework, which is general for all labeled transition systems except for the last part, which is about context, which might only really make sense if your states are processes, terms that describe programs or are programs where you can talk about a subterm appearing in some context, which is the part of the term that's around it. So we have looked at up to methods last time, and in particular, or that was basically the only thing, I showed you the correct or soundness proof, the proof that says that up to by simulation proofs up to the function f are sound if f is respectful. That was the point. So, and now we won't go right to context today because first I want to finish this up to method stuff off because there are some few bits to discuss. And then I would like to go to transition systems. So what is that? We are already talking about transition systems all the time, but well, as you know, we have been talking about simulation systems, which is a more general notion. It means that if you discuss simulation, bisimilarity, these up to variants of simulation, bisimulation, and so on, we always consider an original transition and a simulating transition. So the original transition, this is one transition relation here. This is the one that's considered if you say, okay, given that I can make a step. And the simulating transition is the one that you use when you say, okay, then I can do a simulating step. In a transition system, these are just the same, but we have them in general different, because there is this notion of what we call mixed bisimilarity, which is equivalent to weak bisimilarity, but where you choose the original transition to be the strong, the original transition relation, and only the simulating transition being the derived weak transition relation, because it's simpler to reason in this setting. And maybe we will even get to that, but before we will get to this transition system theory here in our development, which is just a special case that these two are equal. And in this case, you have some more properties holding. In particular, you get a reflexivity of bisimilarity. This is something I always assume to hold, but in fact, it only holds under certain conditions, and the sufficient conditions that these two are the same. So in general, if they are different, it doesn't hold, as far as I can see. Good, but where were we? We were here, right? We had this theorem that up to methods are sound. This is what I just said, that if f is a respectful function on relations, and k is a relation on processes or states that is a bisimulation relation up to f, then we know that k is included in bisimilarity. So if something is related by k, then these things are bisimilar. And now we have these things like the commutativity law that I already showed a dozen times. So this will hold in our calculus. So if you compose processes P and Q in parallel, then Q and P can be composed in this order. And these compound processes are bisimilar. And so now if you imagine we do an ordinary bisimilarity proof using bisimulation up to some function f, then we would say, okay, if biparallel Q can make a step, Let me show this here again. Okay, this P is now P parallel Q, and this Q is Q parallel P, right? So we could use this kind, or maybe it's up to thing. So if P parallel Q can make a step, then Q parallel P can make a step. And we get in things that are related by this f of k. And then if Q parallel P makes a step, then P parallel Q can make a step. So if this guy on the left makes a step, then the guy on the right can make a step. And if the guy on the right makes a step, then the guy on the left can make a step. But apparently the second thing is basically the same, because P and Q can be arbitrary processes. And if you just swap P and Q, so to say, then you see the backwards part is the same as the forward part. And of course, you don't want to redo work. And then, of course, you could write in your proof, okay, that's the second, the backwards stuff somehow follows from the forward stuff. But it would be good to capture this once and for all. And this is what we see here. So the goal is that to have this symmetric up to is sound lemma, which assumes again that f is a respectful function, but it also assumes that this relation k is symmetric. So that if you choose k to just include this p parallel q, q parallel p pairs, then apparently it's symmetric. P and q can be arbitrary processes. And if this is the case, then this lemma says, okay, then it's sufficient to prove that k is a simulation up to f, not a bisimulation. So in general, we had for a respectful function f, and k's that are bisimulation relations up to f, we have this inclusion in the bisimilarity relation of k. And now here we have also this inclusion, assume that f is respectful, but if we can, if we know that k is symmetric, this means symmetric, and then it's sufficient to assume that k is a simulation up to f. Doesn't have to be a bisimulation, but well, it is a bisimulation. This is what this lemma shows, and then it can. It's not necessarily a bisimulation, but it's still that we can conclude that this k is included in bisimilarity. And then in this example with the commutativity of the parallel composition that I just showed, we would just be able to trivially prove that our relation k is symmetric, and then can be done by an automatic prover. It's very trivial. And then we would only have to do the forward step, so to say, the forward reasoning. So and how is this done? So assuming that k is a symmetric relation, so this is a predicate on relations defined in the standard library. The p is not because it means sympathetic or something like that, but the p is again just the marker. I think we might have come across that says that this is for the predicate representation of relations. So sym would just be the symmetry predicate for relations represented as sets of pairs. But here it's for relations represented as Boolean functions, predicates. So symmetric, and k is a simulation up to f, then k is not necessarily a bisimulation up to f, but a bisimulation up to f union f dual. So, and what was this dual? This was what we saw at the very beginning, very first code that I showed you was this here, which has some basic stuff on relations in particular. It has this chain function that is the lifting of the relation composition to functions on relations, pointwise relation composition. And then we had this dual construct, which is using this syntax with the dagger as a not exponent, I mean superscript. Sorry. Well, and what does it do? Okay, it's a function that takes a function on relations like this f for the up to methods, functions f, and gives us a function of the same type. And so the dual of f is a function that takes a relation k, converts it, so it swaps left and right, then applies the f, the original f, on the converse thing, and then converses the result. So it's basically working in this dual or converse space, right? So, and for this symmetry thing here, we need it. So K is not necessarily a bisimulation up to F, but up to F union the dual. So if K is symmetric, so it's this from line here, then we have K converse is K, right? This can be even used as a definition of symmetry of a relation. It's not a definition that's used in the standard library, but it's can be easily concluded. So we use the BLAST reasoner, which is this classical logic reasoner, and pass it an additional elimination rule. So it considers a set of standard rules that can be extended, and we can on the fly provide additional introduction, elimination, and destruction rules. And it uses this elimination rule simp E, which basically gives you the information, okay, given that you have something that's symmetric, then I mean it has this typical elimination rule structure, like case distinction, these things. It looks like this. So if R is a symmetric relation and R relates B and A, then if I can conclude from R A and B some arbitrary proposition called thesis, then I can conclude thesis. And this is this kind of elimination rule style. So if you apply Curry-Howard to this, then it is this continuation passing style. And this boils down to representing an existential quantification, which you don't have in Isabelle pure, in the pure logic, this core logic on which everything else is built. So it basically means that, well, you don't even have the existential quantification because you don't have a universal quantification here. So it's equivalent to just saying from R, B, and A, therefore is R, A, B, at least in classical logic. It would be equivalent, maybe not in intuitionistic logic. But the point is that it has the structure of an elimination rule, and you can know, okay, if something is symmetric, then it means exactly what symmetry means. If it relates B and A, then it relates A and B. So this is what BLAST may use here, and then we can conclude, okay, if you have K being symmetric, then K converse is K. And then with the fact that K is a symmetric relation up to F, we can show that it's a bisimulation up to this union, and I think we need this union. Let me try this out. That doesn't work, right? So I'm wondering a bit now why we need this union. Well, what does symmetry mean up to F? It means that K progresses to F of K. So, and now K is the same as K converse, all right? So, can we do this here? No, not really. So just to, I don't understand that. Ah, it's just so. Yeah. So K being simulation up to F means that if K is equal to K converse, that also this is a simulation up to F. So it progresses to itself. So where's the right arrow? No. So we have this, and here we have an F. So this is what we have from this equality and this fact. Well, but what we want is that what we want is exactly that K is some sort of bisimulation relation. And if we would leave out this F, this dual of F, and just say it's a bisimulation relation up to F, then it would mean that, so now we have to really look at the details. Bisimulation up to F means K exactly bilaterally progresses to F of K. And the bilateral progression is this progresses to this unilaterally, and the converse progresses to the converse of the whole thing. And that's the point. So if you would just have F here, not this dual F, what we would have to prove is that this also progresses to this. Now that's something different, of course, because here this binds stronger, this inversion or conversion. Here we form the converse of K, and here we form the converse of the whole thing. And so there's a mismatch. However, this guy is the same as the following. I hope I now get it right. So if we represent this as a dual of something, then this something must be the dual of that, because duals are idempotent. So it must be the dual of F K converse, and dual means we put the dual outside, and oh no, I'm talking nonsense now. What I'm after, let's do it this way, is this. What's that? So this is Fk converse, yeah, according to the definition, and this conversed, right? Should be. I mean, we can see if this can be proved. Yep. So, and we see this here is this here, and I'm a little bit lost. Maybe someone can help me. It's some time ago that I've written this stuff, and it's very confusing. And I had different attempts.
I think you want to write that this is equal to F dagger K, all of that inverse.
Which one is equivalent to which?
So F K inverse is equal to F dagger K in parentheses inverse.
So I put an inverse here on both sides. So this removes this one, right?
Yeah, exactly. I assume this is what you want.
Yeah, but what does it give us? So we know K inverse goes to this unilaterally, and this is what we have here. And so we know that K inverse unilaterally progresses to this inverse, right? And so this means that this is, so to say, the backwards part of a bisimulation up to something, and the forward part would be K progresses to F dagger of K. So it's the backward part of bisimulation up to F dual. Why what we have been given, the sim F K here, is the forward part of bisimulation up to F, not F dual. But the bisimulation up to F is always also a bisimulation up to something larger than F, because if we progress into something F applied to K, and then we progress into something large, then we also progress into something larger. So if you just take the union, then the F covers the forward part and the F dual covers the backwards part. So the union covers both of them, and then we have the bisimulation. I hope this was reasonably clear. Yeah. So this was also something that I fiddled with. So I wondered, at first I was on this trip that I wanted to require some special properties for the F. I think that F dual is the same as F or so. Then I discovered it's not necessary, even if the F is not so nicely behaved. What we can do is we just don't say that K is a bisimulation up to F, but we just include the dual. And this is only a local thing in this private lemma, because here, at the surface here, it doesn't matter anymore. And why is that? Yeah, in fact, we will see. So if we have a respectful F in K is symmetric and we have only the simulation up to F, then we have this inclusion. But first, from respectful F, we conclude that the union is respectful. And this is by this lemma that the union of two respectful functions is respectful, and that respectfulness is also preserved by this dual operation, right? So we had these, all these preservation lemmas. So this is respectful, and if this is respectful, and that is respectful. So respectfulness of F leads to the respectfulness of F dual, and this together again with respectfulness of F yields to the respectfulness of the union. And now we use our custom proof method respectful. So I had shortly showed you that this is this custom proof method, which just basically more or less applies this one here. We haven't looked at that in detail so much. And this just, this key goal is to apply the rules registered as respectful. And these are all these things that you see here. These are tagged respectful here, and so on and so forth. And these are all these preservation rules. So this is the first time we make use of it. So moreover, from K being symmetric and this being a simulation, we have, according to our lemma here, that K is a bisimulation up to this union. But here we have it. The fact that it's not up to F, but up to this union doesn't play a role, because from respectfulness of F, the respectfulness of this union follows. And so everything is fine. This union is respectful. K is bisimulation up to this union. And then it means, according to our general up to soundness lemma, it means K is included in this bisimilarity. So if we reduce the symmetric case where we only have the simulation proved here to the one with the bisimulation up to something. And the fact that it's up to this slightly weirder function is just a local thing. It's not visible to the outside. Okay, any questions? So then let's go on to basically the final part of this theory, this module, so to say. So what we have now is that we have certain co-induction rules, and these co-induction rules are basically this soundness lemma here and this soundness lemma for the symmetric case here, but written in this more logic-oriented style, so not with inclusion of relations and all that, but also the definition of what bisimulation up to F means is spelled out here. And why is that? Because this way it gets the shape of a co-induction rule and can be used with Isabelle's co-induction proof methods. And typically you need to break it up into this explicit style somehow, anyhow, if you want to do this fundamental proof where you really go through the different cases. I have this kind of process. What transition can it do? How can I simulate them? Do I get into something that's related by F of K? So I have to have this anyhow in the end. And I want to tell you a bit in general how Isabelle handles co-induction proofs. And let me show this first with the co-induction proofs that are possible directly based on this definition of bisimilarity, which is a co-inductive definition. So what this bisimilarity definition says is that, okay, test a single rule. P is bisimilar to Q if for all actions alpha and all P prime into which I can go with alpha, there exists a Q prime so that I can go with alpha to Q prime and the P prime and Q prime are similar. And same for the reverse case. So if I have a Q prime into which I can go from Q, then I have a P prime such that I can go into it, and these are bisimilar. And this is really the spelled out form of these rules. And co-induction says basically that gives you the largest such relation, which is what the bisimilarity relation should be. And if you have this co-inductive statement, you get this new constant bisimilarity, which is your relation, and a bunch of theorems that are proved automatically for you, because they should hold actually. If they don't, then there's a bug, but Isabelle still proves them automatically. And these you can show with print theorems. There's a whole bunch of them. And in particular, there is this co-induction rule. So this is a fact, something that's proved. I can show you this separately. It's called bisimilarity co-induct. And it's this one. So remember, question marks mean that these are kind of free variables that you can think of as being universally quantified, so-called schematic variables. So it says, if you have some relation X, this corresponds to our K in a way. In these proofs, by simulation proofs and so on. So this is the theorem generated from this definition. And it resembles somewhat these rules, but it captures also the fact that you get the largest such relation. So it says, if you have some relation X, which corresponds to the K, and then these two things, x1.0 and x2.0, which are kind of our P and Q, well, maybe I can make the names different. I just say don't show this bisimilarity co-induct, but show it with some substitutions. So X should be K, and X1, can I write it like that? Maybe not. I have to fix that perhaps. This is what I thought. I think I have to use quotation marks here because of the dot. It also doesn't work. I'm really disappointed. Maybe like that.
Can you not apply the theorem just to?
Yeah, this is what but I can use that off thing, which is just where it's just positional, and this should also work. Yeah. Okay, you have this orange thing because K, P, and Q are not really known, but I hope this doesn't bother you. So now we have it a bit more user-friendly. So we have this K, P, and Q, and for all such things, if K relates P and Q, then, okay, for all x1, x2, which are related, there exists P and Q such that they are equal. So this is because of this auto-generation. It makes it a bit indirect. So basically, this X, you can skip this for all x1, x2. These are just P and Q, right? No, actually. No. I'm slightly confused. No, the for all cannot be skipped, but this existential thing can be skipped. There exists P and Q such that they are equal to x1, x2. So it's basically, of course, they exist, and P is now just x1 and Q is x2. So for all x1, x2 that are related, we have this statement that if we now think P and Q are the same, we have that for all x and xa such that I can transition, there exists this Q prime. And finally, I'm again in this relation. Maybe for now, please skip this part. I will get to this soon. Just ignore it for now. And then you have a typical co-induction rule. You pick a relation K and prove that if something is related in K, then if you can make a step with P, then you can also make a step with Q to Q prime. and your P prime, this X is the P prime and the Q prime are related by K, and likewise in the other direction. And this is really what we had here, right? So it says, okay, so the premise says that for all P and Q that are related by K, if you make a step on one side, you can make a step on the other side, and you are again in something that's related by K. So this is basically this part up to here. Without this or here, I will get to this soon. And now it says, okay, if this is the case, then P is bisimilar to Q. And this is exactly this idea of a bisimilarity, the standard bisimilarity proof based on bisimilation. It says if K is a bisimilation relation, then, and it relates P and Q, then P is bisimilar to Q. So this means if K is included in bisimilarity, it's just not in this point-free style now. There's now just this thing here that it allows you, permits you that on this right-hand side here, P prime and Q prime are not maybe in this relation K, but they are on the bisimilarity relation. And that's quite clear. Because if you get into something that might not be related by K, but it is in this actual bisimilarity relation already, well, then, of course, I can go on with the bisimilation game. So that's also fine. And that's always the case that this shortcut is permissible. Therefore, the implementation of this co-inductive predicates generates rules that allow you this shortcut. So if we do bisimilation proofs in the standard way where we don't have this shortcut, it's so to say a bit limiting, but that's not a problem because in the end we are using bisimilation up to some function f, which is more powerful. And as a certain up to method, we have this constant, what was it? This constant bisimilarity here, where we just say f of k is just a bisimilarity relation. This is exactly saying that the P prime and Q prime, they must be bisimilar already. So that's what corresponds to this shortcut here. And then we have this preservation of respectfulness by the union, right? So this, where we have this directly related by K, this corresponds to F being the identity, which is a respectful function. This corresponds to K being constant bisimilarity, and this whole thing corresponds to F being the union of the two, and this is respectful. So the bottom line is that what Isabelle generates automatically for us has this nice shortcut facility, but since in the end we will not have bisimilation proofs, but bisimilation up to some F, and we basically cover this, what we have here, right? So this is just a particular F for a particular up to method, which is identity, union, or join constant bisimilarity. So, and since we have other respectful functions, the up to proof method is, or proof technique is more powerful than that. And so in the end, we don't really use this co-induction rule very much. We use it basically just for two things. And one is here where we invoke the co-induction proof method. It uses this rule. This is when we prove that bisimilarity is symmetric. And the second part is when we prove that bisimilation is in bisimilarity. And that's not so surprising, because bisimilation and bisimilarity really means that if we have proved that K is a bisimilation relation corresponding to this diagram here, then we know K is included in bisimilarity. But this is pretty much what the generated co-induction rule already says, except that the generated co-induction rule has this shortcut. So in this proof here, bisimilation and bisimilarity, when we use the co-induction rule that was generated for us, then we basically just ignore this shortcut possibility and just care about this left part here, because we can later recover it through the up to methods. And later we only refer to this bisimilation in bisimilarity lemma. So let me show you this again. So this was here in this theorem, blah, 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 blah. This is not what I need. It's here in this soundness theorem, right, that we saw last time. There we finally use it, and therefore indirectly the generated co-induction rule. And the idea behind this development is that we will never again, except in these two cases here, we will never again directly use this co-induction rule, but later we will always refer to our soundness, the soundness of bisimulation up to some respectful function f. But for this, we will have these alternative phrasings in, so to say, pure logic that I just showed you, these ones here, which are co-induction rules. So these are just more powerful co-induction rules than the generated one. Generated one only gives you the shortcut possibility, nothing else in addition. Here we have up to arbitrary respectful functions f. So in the end, we have then proved these powerful co-induction rules based on this not so powerful but automatically generated co-induction rule. So, and this is here, if you want to do co-induction proofs directly based on this definition, then this fact that's given to you, proved for you automatically, this is actually the key thing. And then there's this co-induction proof method. And this basically adds some stuff around this bare fact. So this co-induction proof method is not really what does the actual co-induction proving, so to say. The essence of a co-inductive proof is captured in this fact that already this definition of a co-inductive predicate gives you. If you have this fact, and you could, I think, I will try it now, do co-inductive proofs in a kind of manual style, and the co-inductive proof method just invokes this fact and makes your proofs, allows you to have your proofs be written in some bit nicer style. So, and I would like to show you that based on this second lemma that uses the co-induction method. So this is that bisimulation is in bisimilarity, which is, as I said, basically the statement of the co-induction rule, just that this uses this point-free style and this ignores the possibility to shortcut. So what do we have here? We have, okay, we fix some particular P and Q because we now go away from point-free style and assume that K relates P and Q. And then from the fact that K is a bisimulation relation, so that we can play this bisimulation game, we show that P is bisimilar to Q. So the point really is that. So we want to show this inclusion. And if I say proof and don't write anything behind it, then it will apply a standard proof method. And in this case, it depends what it applies on the goal, which is this in this case. And in this case, it will just go from point-free style to non-point-free style. So if I say proof, then I see that my actual goal has changed. Right? It's not K included in bisimilarity, but it's for all X and Y, which you think of as P and Q. If they are related by K, then they are bisimilar. And how do I prove such a universal quantification with an implication all in Isabelle pure? Well, I can again use this outer syntax prose style. I say fix P and Q. This says that in the end, I prove a universally quantified thing, a statement with universal quantification on the outside. But here I just say basically, okay, I assume we have a particular P and Q. I can also choose different names different from these. And then I can refer to the P and Q. So I don't say what P and Q are. So I prove a universal statement. However, I can just now refer to P and Q. I have some specific P and Q, whatever this is. And I assume P and Q, this says that we prove implication in the end. So and now I can, again, it's like with this fix, I can refer to this, I can refer to this fact and use it at later points. And then I just have to prove this, what's on the right-hand side of the implication here. So, but how does this work? So I say with bisim K and with this blah, blah, blah says that I use this as a fact, but also the previously stated fact. And the previously stated fact is nothing that's proved, but this is this assumption, which I can assume this because I'm only about to prove this implication where we have this premise. So if we go here, we say that P bisimilar Q is our goal. And what we can use is this bisim K. This is the assumption that we pull in here with the width. The width at the same time also pulls in the previous statement here, sorry. And this is K relates P and Q. And now I say by co-induction blah, 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 sim plus. So in principle, I apply two proof methods, this co-induction proof methods with some parameters, then the sim and then the blast. So, and now I want to show you what this creates as intermediate facts, and I can use this imperative apply style to show you that. I say this, I say apply sim, and I say apply blast, and then everything is proved, and then I could say done, and then this would be finished. So instead of this nice structured by blah, 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 I could use this style also. And this is good if you want to develop your proof method invocation in the first place, because you can see the intermediate sub-goals. So the application of the co-induction method gives us that. And this is basically, what you basically see here is almost the co-induction rule, right? But there are some important differences. So first, it saw that when we were here, we have this bisim K, and it drags this in as an additional premise. So that's the cool thing. And then you have this thing, and this is basically the co-induction rule. The co-induction rule is premise, right? Because we want to prove this bisimilarity thing here. And now let me quickly get this. No, this was wrong now. The co-induction rule. That's this one, right? The co-induction rule, if we fix the variables, the three variables here to be K, P, and Q, it says, okay, if K relates P and Q, and this thing here holds, so that from K relating something, blah, 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 and then we have this, that if you can make a step, we can make a step on the other side, and this is related by K, or we have this shortcut possibility. So this has two premises. First, that P and Q are related by K. Then the second premise, that I can play the bisimulation game with the possibility of shortcut. And the conclusion is then, okay, if you have that, then things are bisimilar. And now the co-induction proof method sees that the P bisimilar Q is what we want to prove. So it says, okay, that's good, because this proves something like that. But actually, initially, we don't have our variables fixed. We see that the co-induction rule says, okay, you get it for some x10 and x20. And the co-induction method figures out, okay, if you want to prove P is bisimilar to Q, then I must substitute P and Q for these variables. So it already knows what these variables are. But there's another free variable, this x here, right? And so the question is, what this x should be? And now it sees, well, what I have as a premise is this K relates P and Q, and then it can figure out that it would be the sensible thing to let the X be K. So what the co-induction method does in particular, it not just sets these x1, x2 variables, but it sets also this relation K variable, which is called X here, to the particular K that we are using here. And I think this is something that really an ordinary application of a rule wouldn't do. So you could just take this fact, bisimilarity.co-induct, this co-induction rule, and use an ordinary rule application method. But this wouldn't, I think, know what this X should be. So you would have to be explicit about that. And will be even more important later if we use the co-induction proof method for up to rules that are at the end of this theory, because the co-induction method is actually much stronger. It can even figure out if you have a goal that it's a bit more complicated, like this. I maybe should give an example. Or maybe I will show you particular examples later when we actually make use of that. Because what it can do, as Terry's in principle, if you have something like this, I had an example all the time here with a parallel commutativity, like this, then, doesn't work. Okay, then it will figure out, I'm not lucky. It will figure out that it's just not a P and Q, but it's something that has this structure P parallel Q or Q parallel P, and can even cope with that. It will then say, okay, you have two variables, say S and T, which correspond to your left and right hand side, but these additionally have to fulfill a condition that they must have this structure, and then it will mangle the co-induction rule such that you get this additional condition. I mean, it's difficult to show this in this general context, but I hope I think I will be able to show this to you later. And even go so far that if you have something like this law, which I also mentioned already. A moment. So P parallel Q is bisimilar to P parallel R, given provided that Q is parallel R. This was congruence rule or whatever people call it. So here you have not only that the left and right hand side of the bisimilarity statement that you want to prove, that they have a certain structure, this parallel composition, and this constraint that the left sides are equal, they are both P, but you have a condition phrased as a premise about these two terms. And even this is something that the co-induction method can cope with. So it will then say, okay, you want to prove that some S is bisimilar to some T, but there must exist P, Q, and R such that S and T are P parallel Q and P parallel R, and that Q is bisimilar to R. So the bottom line is that if you have particular processes for the left and the right hand side here, and you maybe even have conditions on them phrased in terms of premises, the co-induction method is smart enough to figure out what your relation K must be, right? So here it was simple. The K that you should use for the co-induction method, which is called X here, this is just our K that we have here. But if you have a more complicated goal, something like this below here, then the co-induction method will really construct on the fly a relation K that relates exactly the processes P parallel Q and P parallel R for any P, Q, and R where Q is bisimilar to R. So it will construct you some lambda term that expresses directly this relation that relates all such processes. And that's very convenient, because if you want to prove lemmas like this preservation lemma here, you don't have to first say, okay, my relation K that I use for the proof is that, and now please use this relation K. But you just say, okay, this is the statement I want to prove. Prove it by co-induction using the co-induction up to something rule. And then this co-induction proof method will not blindly apply this rule, but it will figure out on the fly what your relation K must be, so that it just covers what your goal says, and it will use exactly this as your K. And that's quite powerful. So in this case, I don't know whether I would even need the co-induction method, because I don't need this power really. I could probably say, let me try, I just apply the bisimilarity co-induct rule as a rule using this rule proof method, which really just very simply applies rules. And we see it doesn't work. And maybe I can help it a bit and say where the x is my k. It still doesn't work. And fix the p and the q. And it also doesn't work. Also, I'm sorry, I thought I could make it work. And with the intro method it works. So I just say, neat. I use this co-induction rule now, not really as a co-induction rule, but just as an introduction rule, something that introduces bisimilarity, right? Looks like this, would be an introduction rule of bisimilarity. If I use it as an introduction rule, then I see, okay, from bisim k, I have to prove that from this follows the thing itself. So we see now our goals become a bit more clumsy. I have this trivial thing which the co-induction method would produce or just discharge on the fly because it's more powerful. But then I basically have this thing that if k is bisimilarity and this is related, and yeah, we see again another mismatch. Now we are forced. Yeah, so we are required to prove this bisimulation game under the assumption that x1 and x2 are related by k, where this can be in principle anything, but and this cannot be proved actually, right? So the introduction method really doesn't work. So bottom line is, maybe generally speaking, that the co-induction method generates a k on the fly, which is not really necessary here, and does maybe some other fanciness, and the intro method does yet different fanciness. And I think if you would go down to some bare rule application, you could tweak things such that you don't need the co-induction proof method. I just cannot get this now on the fly. So the bottom line is that the co-induction proof method does not by itself have the wisdom why you can do co-inductive proofs. This wisdom is in this bisimilarity.coinduct fact that the co-induction method just uses internally. And it's this one that contains this wisdom. The co-induction method just makes your proof more fancy, so that you don't have to manually apply this rule and tweak the parameters k and p and q on this stuff. Okay, maybe the problem was no, this also doesn't work. Okay, so are there any questions? I think there's something in the chat. Javier says that's fantastic. Anyone who have ever tried to prove a non-trivial bisimilarity by coming up with a suitable bisimulation k will absolutely love it. Of course, I also find it fantastic, but I must point out that Isabelle is not smart here. It just mechanically derives the relation k from the proof goal. And in our previous implementation of our previous calculus, actually the implementation, this was not the right thing to do because we didn't have up to methods. And as a result, we couldn't pick our case such that it covers just the term pairs that we are interested in. But we had to enlarge this k to basically cover all these f of k's and so on, which is what now the soundness proof of up to does automatically once and for all. So in our previous development, this wasn't possible to use the co-induction method. I didn't know that you could use it this way, but it also wouldn't have been possible because the automatically generated relation k generated by the co-induction method would have been too small. It wouldn't have covered this clutter that's up to especially exactly allows us to avoid. That's the point. Up to allows us to avoid the clutter. Therefore, we can shrink our k to this just minimal relation which the co-induction method creates automatically. And it's very convenient that you don't have to write this explicitly. You just get the right k chosen, and then will create your sub-goal that you have to prove, this bisimulation up to game, and it will just directly use this relation. Okay, great. So now What next?
It's actually a bit different though, right? Because the like co-induction doesn't choose K, but instead it chooses K and the fact that K is bisimilar.
Yeah, but you have to pick a K.
Yeah, true. But so if we just look at the proof state, then the context exactly contains the fact that K is bisimilar and that we have K relates P and Q.
Mm-hmm.
And so co-induction just picks those two facts basically together and puts this into the X.
But that's not quite how it works. So the co-induction proof method really looks at the goal and at extra premises and mechanically generates the K to use from it. And this happens no matter whether we already have the statement that K or whatever is a bisimulation relation or not. So in the typical proofs that later use our up to methods, we will just have our statement like this. This statement like here, there's a preservation without having any bisimulation relation statement, any bisim already established, and we will just say apply co-induction, and then just from this goal with this premise here, it will derive the K and then generate the additional proof goal also that this K must be a bisimulation. So you get another sub goal to prove. It's just that in this particular case, once it has established that the K to use is exactly this K here, it will generate a sub goal bisim K, but then it discovers this is already in the list of premises and this will be discharged automatically. But in general, it doesn't work like that. So you can just have this additional sub goal to prove this bisim something. So it doesn't take the existence of this bisim K into account when coming up with what the relation should be. But that's fine for you.
So in the case with this parallel composition, that wouldn't influence the relation though, right? That just means that this P and Q would have to be picked as P parallel Q and P parallel R.
Yes. So you basically would get the relation that says, okay, given some S and T, when are they related? Well, they are related if there exists this P and Q such that Q is bisimilar R and S is this and T is this. This would be the relation that it would generate. Okay. But here it has this additional premise bisim K. This probably doesn't count. I mean, we can just remove this out of fun.
So if you look at the proof state after the first, like after you apply co-induction.
This one.
Yes. So here the X is now bisim K and K applied to P and Q.
No, the X is just the K. So this bisim K here comes from the fact that we have passed this into this proof. It's actually not this chart. No.
I think this results from instantiating the bisimilarity.coinduct with
No,
conjunction.
I think what happens is exactly what we have here. If you have this additional condition, which was Q bisimilar R, it ends up here. I must say I'm slightly confused. Okay.
So what happens if you put the line back where you applied the co-induction manually, but instead of having X equal to K, you do x equal to lambda AB by sim k and KAB.
Well, this happens. But also the intro method might do some little bit of fanciness. I'm not sure if this is the pure thing that we get.
Yeah, maybe not. No, if you replace k here in the where clause.
Only k.
Yes, and so you replace
that
k.
Didn't work.
No.
It was the rule statement that didn't work. Yeah, I see.
Keep the P and Q, but replace k with lambda AB.
Or CST.
Okay, thing. And then you do bison k and KST. I think this is then.
You're a genius. No, but I'm not sure. No. But you get this one here. Also, you get this one here.
Okay, so the inner clause, like after the exists, looks like what's generated from the co-induction, but yeah, there is an extra thing.
And there's another thing that's important. Maybe I will replace this by k here. Maybe it makes it more visible. If we take this one, then we see I skipped over that, but it's actually an important issue. We see, okay, k must relate p and q, but k must also relate x1 and x2 for all x1, x2. So for all x1, x2, if they are related, then we can play this game, and then the resulting things are related. This is actually what we must have, right? So it's not just that for our initial P and Q, we have this by simulation game, but for everything that's related by K. And this is interestingly something that the co-induction method, I think, would not generate for you, because if you would just say, let me try this, apply co-induction, because the co-induction method looks at the goal, and it tries to generate a k that corresponds to the goal. Now the goal uses this fixed p and this fixed q, right? And so it would generate a relation that just links this p and this q. So it would say, okay, if p and q are in k, I must be able to play this by simulation game. And the result of this by simulation game, this would be this p prime here, this would be q prime, and this is p prime, this would be the q prime. They must be again p and q. So it requires us that if you start with p and q and make one of this transition and simulating transition step, that then we end up in p and q again, and this would be wrong. Or generally, it would be too strong a requirement. And this is because co-induction is precisely smart and looks at the goal and creates the k from it. In this case, it would take the k to just relate this p and this q. And if you want to have it for any p and any q, then we must say this arbitrary pq. So if you have the simple goal and put arbitrary here, then we recover what a simple rule application would do, basically. But in general, it's good that co-induction looks at the goal and creates the k on the fly. Okay, any more remarks?
Well, I think, I mean, this point that Andre raised, it looks to me as if there is, well, I have the feeling that it might actually work, even though it didn't now. But I don't have the basics of you know, going through the details or even explaining myself.
Yes, so in both lines where you just applied co-induction, it looked to me as if X was instantiated with this, basically with this X I dictated, right? Because in both cases, in the last lines,
Yeah,
there
really, we have
Bison
K. You're right.
and
You're right.
KPQ.
You're absolutely right. Well, it's a bit more complicated because it has this existential blah blah blah, which comes because the co-induction, I think, is more general.
Yeah.
But it's basically says there exists something blah blah blah, which is equal to that. So it's just that. So it's really Bison K and blah and yes. And what do we have here? It's KPQ. We have these two premises. Yep. No. Yeah, it's basically the same. It's just that we have this trivial goal here, which the co-induction method discharges automatically. Absolutely, and I think this is what I at one point speculated about. I said if we have something like this here, this preservation law, then the K that's constructed relates this P parallel Q with P parallel R, provided that Q is bisimilar to R. So it takes the premise into account. And here it will just take this premise bisim K, which actually is not about P and Q, which is, so to say, static compared to this. Still, it's a premise. It will take this into account. And so what actually happens is that this is not kind of considered separately, but sorted into this part even where it just doesn't harm, right? Because you don't need it. Where you need it is here, that you have it as a premise here. That you must show that it's bisim K here is trivial because it doesn't refer to P and Q. So given that it's you have it here, you have it here. That's absolutely right. So it becomes kind of something that we considered every step, every bisimulation step, which is a bit strange but works. Right. So actually, we should be able to replace this co-induction blah 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 by this, and that's neat. Thank you, guys.
Can you do this without the intro?
And I think this other no, for some reason not.
Oh.
But I could now skip this thing, and now it doesn't work because I have this additional goal. I have one more. Whoa, it works. Why does it work? That's interesting because the simp only discharges the first goal, so the blast is able to discharge the second one completely. So if I use co-induction, I should be able to skip the simp. The simp was there to simplify matters, so it expands the definition of this bisim here, right? And then blast will do the actual solving. But now it seems that I can skip this. But I can't. So there must be some subtle difference that makes this not work if I use the co-induction method. So
interesting.
Yeah. Sometimes these things can be subtle also because these methods do search. And I mean, for BLAST, it tries to do an exhaustive search, but I think it can get stuck because it does depth first search. For SIMP, it's such that it's just is brute force and it doesn't do backtracking or something like that. So you must, SIMP does this rewriting, equational rewriting. You must take care that preferably your rewriting system is confluent, because otherwise it can depend on luck. If you update to a new Isabelle version, which comes out every year, then maybe your proofs don't work anymore. So you should be careful there. But I think we have got some insight, and it seems that really this here is the relation that the co-induction method is creating. So thank you for the help. It's a bit embarrassing to get to that, but yes.
I mean, I've been thinking about these things for some time as well. So it's I'm familiar with this in other languages.
But the good thing is, we have already discussed quite a few bits about co-induction in general. In particular, this bit is important for me, that you can have these complicated goals, and the co-induction method will figure out the relation K to use, which is very powerful and is something that I wanted to cover definitely. So let me remove these experiments, go back to this thing here. So this is the co-induction proof method, and if you don't say anything special regarding rules, then it picks the rule from the goal. And since the goal is a bisimilarity, it says that it picks the bisimilarity.co-induct fact. However, you can say also as a parameter rule colon and then some fact, and then it will pick this fact as the co-induction rule to use. So you can't use the co-induction proof method with other co-induction rules. And again, you could apply these co-induction rules, these alternative rules, to some more primitive proof methods, but the co-induction method has this fanciness like figuring out the K in particular. And this is what we do in the end. So we have, for example, our up to is sound lemma. F is respectful and K is a bisimulation up to F. And this is now the important thing, which goes beyond the standard co-induction rule for bisimilarity. We have this, then K is included in bisimilarity. Now we can break this statement up so that everything becomes, this becomes a co-induction rule. So, and this is what we have here as a corollary. So let me get up to a sound into this part below. So this is up to a sound, right? If F is respectful, K is bisimulation up to F, then this is included. And now we have this here. Let's not be concerned by this thing above here for now. It assumes that K relates some S and some T. So this is universally quantified. Comes schematic variables. So if K relates something, so we are now going to non-point free style. And we have respectful F, like here. And we have bisimulation F up to F of K. This we could state as another premise, but I chose to unfold it, so to say, because later, this has nothing to do with this becoming a co-induction rule, but later if we do our proofs, these proofs where we directly go down to the transition system as it is defined for our particular calculus, for our particular notion of bisimilarity, then we need to reason about these transitions here explicitly anyhow. So it's actually better if this rule here already breaks it up for us, then we don't have to do it manually in every proof. So this is basically, should basically be what bisim FK means. So this was defined in terms of bilateral progression, and this is in terms of unilateral progression and conversion. And unilateral progression was defined in terms of relation, inclusion, and composition. And this is again defined in standard library in terms of logic. So there's quite a bit going on underneath. And this is what it means in the end. I even have replaced the universal quantifier by something, by this Isabelle pure universal quantifier. So it says, okay, for any action, and any ST, and S, sorry, yes, by sim is this, and any S prime into which we can get, that if K relates ST, and S can go with alpha to S prime, then there exists a T prime, such that we can go with T to T prime with the alpha, and S prime and T prime are related by relation F of K. So this is everything spelled out, and this is for the backward selection. So then we can deduce that S is parallel bisimilar T, sorry. Okay, and we directly use our up to is sound lemma, which you see here. We apply it to this premise respectful F that we get here. So to say, this is important because BLAST cannot figure out that it should take this and apply it here. So we do it manually. So then we get this part here. And then we instantiate our variable K, because also BLAST cannot figure that out, to our particular K we are using here in this statement. So if we go here, we get this tweaked thing by simulation. We have the K specialized, and we have the F specialized. This comes from this respectful F here, right? Goes up to sound. refers to respectful schematic variable f, but if you apply to respectful our f, then this f is already instantiated, and then we just instantiated the k, then we get this part with everything nicely instantiated. So bisym fk for our k, and then we get this. And then we use the assumptions number 1 and 3 to 4. So everything is except the respectful f. So these ones, and then we can conclude this just by BLAST. So, and it's basically trivial. So if we unfold the bisym definition, then it's basically this second last and last one. And if k relates s and t, this corresponds to the left-hand side, then of course s and t must be related by the bisimilarity relation. So this is our corollary, which can be used as a co-induction rule. Why? Well, because of the structure that it has. It's very similar to the bisimilarity co-induction rule. Oh, sorry. So let me show you this one again. So we have this rule, this up to rule. But before we had our bisimulation dot co-induct rule, and that's of course not bisimulation but bisimilarity. And here we go. So the first thing looks very similar. This is that these things must be related, and it's important that this comes first, I think, otherwise the co-induction method wouldn't work. So, and this is KST. And here we just have this additional condition that's different to this one. But this is fine. The co-induction method can cope with that. It just becomes in your it just generates, it just basically pulls this through and gives you this as another sub-goal to prove. So additional premises are actually fine in co-induction rules. And then we have 2 premises here in our nice up to rule. But here we had a single premise, but I think this should boil down to the same thing. We say, if this is related here, and there exists the things that are equal, which basically means that we can drop the exists, then we have this bisimulation game. So we can simulate in one and in the other direction. Okay, here we don't have the shortcut anymore, but we have this f, so we have up to. This makes it more powerful. But here we have a single implication. So if this is related, then we have this simulation in one and the other direction. Here we break this up. We say, okay, if it's related, we have this one thing, and if it's related, we have the other thing. And this, I believe, makes it simpler. And why? Because if the co-induction method sees this up to rule that we have proved, then it sees, okay, there are 2 premises, so it will create 2 different sub-goals for you to prove, and that you can prove one by one, while here you would have to prove basically 2 things in one go, and this would be less convenient and the proofs would become more ugly. So we have also done some tidying up in the course here so that we get some really nice rules that are very convenient to use. Was there a question in the chat? Yes, there was, but some minutes ago, but there was some other thing. I don't know why. Okay, yeah, so this is our nice, polished and co-induction rule that has this feature of up to and needs this additional thing here. And now,
sorry, that's just a little remark. You can also see that some for all and implications in the whole logic were changed to the for all and implication of pure. Yeah.
Exactly. So here it created this bundled thing with the and, right? And this must be and it has this exists. So exists only exists in whole and not in pure. So everything under it must be of type bool, not of this prop type of Isabelle pure. So it must use the Isabelle whole connectives. But here I was able to use the Isabelle pure and the Isabelle pure implication, which is here. This is what corresponds to this. And this is more convenient in the proofs if you want to really use these things as separate facts that are assumed, and then you just prove the thing on the right. This is what you also had with these fixes and assumes. This works with Isabelle pure constructs, not Isabelle whole constructs. And where does it come from? Because also here we use the pros. We use assumes this and this and this and this, and shows that, and this uses under the hood these Isabelle pure connectors for these guys. But okay, here I did it manually because it's a premise. So inside the premise, I manually used the Isabelle pure connectors, which makes it more easy to use later. So, so this is our nice rule. More remarks from you, Javi?
No. Thank you.
Yeah. And then I have this funny case names, and this is also for convenient use of the co-induction proof method. You have seen already this. There was something, right? We have had this. Yeah, in the induction proof, we had this thing that he said proof induction n. We got two subgoals, 1 and 2, and then you could use this case stuff here, and this case stuff names the cases, and it automatically fixes and assumes certain things, which here is automatically done on the grounds what induction means, actually. So that we have these case names, and then we have the automatic fix and assumes. I think this is even independent of whether this is an induction or not. So here, for example, in the successor, you don't have to prove an implication. So actually, we have to prove this implication, but we saw that the premise is available as a fact, and we only have to prove the conclusion as our goal in the end. This is what the case is doing automatically for you, and it allows you to name these things. And it would be nice to have this also for our co-induction proofs. We do have it for the bisimilarity.coinduct method because it has these case names attached to this fact. And we can do it for our own rules. So the point is this: the co-induction method will always get rid of this first assumption, so we don't have to and should not name that one. Why is that? Because it will create the... No, it actually won't. No. Will? No, it will. Because it creates the K exactly that it fits this S and the T using certain premises that we list in addition. So it's trivial that K relates to S and the T because it was constructed to relate to S and the T. And it's very directly is true. And therefore, the co-induction method will not just create a K, but discharge this assumption because it has this K exactly tweaked such that this assumption holds trivially. So it has only this, and this left. And this is what the case names refers to. So we say that these premises have the case names respectful, forward simulation, and backward simulation. And if you then have an actual proof, actual co-induction proof, we will have these case names at our disposal to be used. Then we can just say case respectful, case forward simulation, case backward simulation. And we will automatically get these fixes and assumes. We get nicely structured proofs. It's very beautiful. I would like to show you something, some example, but at the moment I think, I don't know if I have one. I think maybe in this week transition systems thing, but maybe not. Let me check. No. Or in the weak mutation system thing. Unfortunately not. I mean, I have an example of the symmetric case in the actual calculus development. I can show you this to you in a minute. So this is for making our proofs really behave nicely, that we can use this case construct. And so it becomes very convenient. So let me first show you this symmetric up to rule. This is just this symmetric simpler statement. It's of the similar form. K relates S and T, and F is respectful. And then we just have, in addition, this point that, one moment, let me show you this. We use this lemma symmetric up to is sound. This is what I showed at the beginning today. to you. It's the thing, okay, F must be respectful. In addition, K must be symmetric. And then it's sufficient to just assume simulation or bisimulation in order to get this inclusion. So we have to additionally, besides respectfulness, state the symmetry. And also here, I have already broken it up to bare logic, Isabelle pure logic, actually, because this is more convenient for the provers, because often the generated K is trivially symmetric, and you can just simply solve it with a simp or a blast proof methods, and then it's better to not use the sim predicate, because then we would have to first unfold the sim predicate or tell the prover that it has to do so. So that's not a nice style if you want to phrase a correctness theorem like this symmetric up to a sound, then this is nicer, I would say. But if you want to have a corollary or fact theorem that can be used as a rule in your proofs, the co-induction rule, then it's better to spell this out, because you have an easier job in using that. And now here we just have this first part, basically. So if only the forward simulation, which corresponds to this simulation here. So, and now what do we have? Basically the same thing. We just take a different lemma, symmetric up to a sound, and apply it again and take the other assumptions. Yep. And now we first have to unfold the definition of symmetry. So apply this defining equation from the standard library, and then we can solve it by BLAST, as it was here. Again, we have case names, respectful, and now we get symmetry in addition, but we have only simulation, not forward and backward simulation, as we had here. Okay, any questions? So then let me just conclude by showing you the symmetric up to rule in action in actual calculus development. Let me check. Where was it? Was it an unnatural play? I proved parallel, not parallel composition commutativity, because I needed it early somewhere. Let me check. Yep. So I think it's already done almost. So need to catch up with the proving. Parallel is commutative. So we see here P parallel Q is bisimilar to Q parallel P. This S means synchronously parallel. So now what we do is we invoke a co-induction proof method. We say these must be arbitrary because we don't go into the same P and Q thing. It's the thing with the same P and Q. It can be a different P and Q. So these must be universally quantified. And now we don't use the co-induct rule of the bisimilarity relation, but we use this symmetric up to rule, which you have just seen, right? The last one. And we instantiate the F. So we specify here what our up to method should be. And this M is up to mutation, which is a generalized form of up to context. And this is just this normal where that you have seen, where we just take a fact and instantiate variables. So this is our co-induction rule. And then we get cases, right? Exactly these. So our proof could have this outline. It says case respectful, and then we prove the respectfulness of this M. And it says case symmetry, then we prove the symmetry of the generated relation K, and then we prove the actual simulation game that this is possible. But what is our K? And we see it here, for example. I think it's basically this here. And you see it's again a bit awkward because this is a very general mechanical derivation, which in this simple case phrases everything a bit indirect. So S and T are related. No, it's actually direct. It's very direct. S and T are related if there exists P and Q such that S is P parallel Q and T is Q parallel P. This is exactly what we wanted. And this is automatically figured out by the co-induction proof method from this goal that we have. We don't have to define our K ourselves. And then we have to prove respectfulness, symmetry, and simulation, and can do so with this case construct. What I actually do, I only have a simulation case, because respectfulness and symmetry, they can be proved trivially by some proof methods, and then you don't have to list them explicitly, but you just say, after the Q and D, you list some proof methods which just discharge the boring cases, so you can keep them out of your nice structured proof in the middle. So our custom respectful proof method solves the respectful case, and BLAST solves the symmetry case, because if you look here, the symmetry case is just this. So, and it's very trivial. If we have all P and Q, we have P, A, Q, A, such Q parallel P is PA parallel QA. This is an injective operator, the parallel. So Q must be QA, Q must be PA, P must be QA. Then obviously this holds, and this can be solved trivially by the BLAST prover. So only the simulation case is left to prove, and then we just say case simulation. And as I mentioned, this case already does automatically this fixing and assuming. So the goal we have to prove is this thing for all blah blah blah. If this holds, we have an implication here, then that holds. But after the case, we have these variables fixed, so we can say, okay, we have a particular alpha and blah and blah and blah, and we can even give them different names. So the small s prime becomes the capital S for some good reason of my naming. And this becomes an assumption. So this is a fact that we can refer to explicitly, and we only have to prove everything from here to here as our goal. So if I go with the cursor here, we see, okay, we have this premise, and then we have to show this as a conclusion, and these variables are all fixed, which this color indicates. And then we do some case distinction on the transition. That's how it works. And I would say it's pretty convenient to do. So typically you would just discharge the symmetry, and at the end, this is automatic prover, and this respectfulness even more so, because we have this proof method which automatically applies this preservation rules, and it's usually such that just from these rules we can prove that our custom constructed function f here is respectful. So, and the only interesting thing is really the simulation case, and this is what we spell out explicitly. And this is how it can look. So it's a lot of case distinction on what a transition is. That's very typical for process calculi. It's already relatively harmless because it's a relatively simple lemma. And now you can try to imagine how it was for us when we didn't have up to methods and we had to take care about some additional clutter. It was not nice. But now we have this. Okay. Thanks for listening. Are there any final questions or remarks? Okay, if not, then thank you for listening again, and goodbye. See you next time when we will finally go to transition systems, and hopefully also weak transition systems, or maybe afterwards. Good. Thanks.